In this class, we will discuss orthogonal sets. What do you mean by orthogonal sets? Consider a set of vectors is given by set u1, u2, u3, etc. This is a set of vectors. And orthogonal sets mean it is defined like this. A set of vectors u1, u2, etc. up in Rn is said to be an orthogonal set if each pair of distinct vectors from the set is orthogonal. That means u I dot or inner product uj equal to 0. That means again for every for all I not equal to j. This is the condition. For every I not equal to j, if the set of all vectors or set of all distinct vectors satisfy this inner product relation, that is ui dot uj equal to 0, then we can say that is the orthogonal set. Orthogonal set. Orthogonal set. Yes, let me explain with this example. That is example 1 show that set u1, u2, u3. These are vectors in R3 is an orthogonal set that where u1 equal to u2 equal to u3. Okay, so that means you have to prove that u1 dot you should take first of all u u1 dot u2, then u1 dot u3 and u2 dot u3, or you have to evaluate these three and verify that whether these are equal to 0. Okay, so the solution is like this. Is u1 u2 u1 dot u1 inner product u2, that's equal to 0. u1 inner product u3, that's again equal to 0. u2 inner product u3 is again 0. That means each pair of distinct vectors is orthogonal, and so u1 u2 u3 is an orthogonal set. So figure 1, if you see, so u1 u2 u3 are vectors in R3 already. We have explained that. So if you represent u1 u2 u3, then you will get these points in 3D space. Okay, u1 u2 and u3, which are forming orthogonal 90-degree with respect to each other. So these vectors form the orthogonal set. Okay, now the theorem number 4, that is, if S we are given a set of vectors, that is S is equal to u1 u2 u3 etc. up, is an orthogonal set of non-zero vectors in Rn. The S is linearly independent and hence is a basis for the subspace spanned by it. Okay, basis. So in this theorem we came across this basis, right? Basis. So we know, if you have any doubt about the theory or concept regarding basis, you should go to that there, and you should recollect that what you mean by a basis. So these are linearly independent set, because orthogonal set of non-zero vectors are linearly independent, that you can prove it. Linearly independent means, yes, solution will be only trivial solution. Yeah. So, and hence is a basis for the subspace spanned by S. So the proof is here. The proof of this theorem for is like this. Considering, let us take, if the is 0 equal to C1 U1 plus C2 U2 plus C3 U3 plus etc. plus CP UP is a linear combination of the vectors in set S, right, for some scalar C1 etc. Cp. That means this is an equation linear combination. Now, okay, now I'm taking another proof that another fact that 0 equal to 0 inner product u1. So if you take the inner product between the 0 vector and any vector, any other vector, u1, u2, u3, etc., up, any other vector, then what you will get is again 0. So this 0 is replaced by this equation. That means C1 u1 plus C2 u2 plus etc. Cp up dot u1 equal to 0. That means that C1 u1 inner product u1. That means like this. By the property of inner product, we have this. So C1 u1 C2, okay, C1 u1 inner product u1 plus C2 u2 inner product u1 plus etc. Cp up inner product u1 again. That means u1 is inner product with u1 u2 u3 multiplied by the scalars. Now what we have, again applying the property of inner product, that means you can take out the constants, scalars or real numbers, then C1 C2 C3 etc. Cp are taken out, and yes, it is said that the u1 u2, actually the u1 u2 u3 etc. up, the set S is an orthogonal set of non-zero vectors in R. That means orthogonal set, just we have came across that u1 inner product will be there in distinct vectors, inner product will be 0. That means u2 dot inner product u1, u3 dot u1, u4 dot u1 etc. up dot u1 all will be 0. Okay, all will be 0, 0, 0, 0. So you will get equal to e1 u1 dot u1. That means u1 dot u1 inner product u1 will never equals to 0. So that is 0, 0 equal to c1 into u1 dot u1. But u1 inner product u1 will not be 0. So that c1 must be equal to 0. C1 must be equal to 0. Okay. Similarly, you if you inner product, you can find out the values of C2. Okay, you can find out the value of C3. You can find out the value of C4, etc. Finally, UCP values can be evaluated by using this method. So you can guess that for the C2, C3, etc. Cp must be 0. That means this equation 0 equal to C1 U1 plus C2 U2 plus C3 U3 plus etc. Cp Up only have trivial solution. That means 0 solution. That means that U1, U2, U3 etc. Up, the set is and is linearly independent. Linearly independent. So linearly dependent. So the definition is that, and also yes, it forms the basis for the subspace spanned by S. That means uh, span of S you have to consider span span of S. That means U1, U2, etc. UP you consider. Then this set U1, U2, U3 forms the basis for this span. Okay. Then we are moving on to the definition. Definition of orthogonal basis. What do you mean by an orthogonal basis? Definition of orthogonal basis. An orthogonal basis, and this orthogonal basis is again defined for a subspace or another subspace, like your symbol basis. Okay, symbol basis you have you know what you mean by symbol basis, but the orthogonal basis means an orthogonal basis. It is again defined for a subspace W of Rn. Okay, is again a basis. Okay, is again your that means the definition of a symbol basis is also a good holds good in this orthogonal basis also, and it's a basis for W's, so that is also an orthogonal set. That means suppose we have an orthogonal set. Suppose we have an orthogonal set like that, like this. Yes, is equal to u1, u2, u3, etc. u3 orthogonal set. This is an orthogonal set. If this forms a basis, for a subspace W, belongs to Rn, then we will call it as this is the orthogonal basis for the subspace W. Okay, that is the definition. Okay, yes. Now we have the theorem number 5, that is yes, let now again consider the set S of all vectors u1, u2, etc. up be an orthogonal basis for a subspace W, okay, of R. It is said that this forms the orthogonal basis for the subspace W of R. For each y in W, that means orthogonal basis means we have a set S equal to u1, etc. up we have, and we have a subspace W, and this forms an orthogonal basis. That means span of set u1, u2, etc. up will result in a y in which belongs to W, or for every y which belongs to W we have a span of u1, u2, u3, etc. up. That means for every y belonging to the subspace W, we have a linear combination that will result, that is C1 u1 plus C2 u2 plus etc. Cp, like Cp up, that will result a y in which belongs to W. That is, and that is the basis. Then orthogonal basis means this set S is a orthogonal set. If the set S is a orthogonal set, that is an orthogonal basis. Okay, so for every y belongs to W, we have a span in we have a span in orthogonal basis. So this set S forms the orthogonal basis. And here what the theorem says that let you set S equal to u1, u2, u3, up be an orthogonal basis for a subspace W of Rn for each y in W. Okay, for each y in W, the weights in the linear combination, that means y equals c1 u1 plus c2 u2 plus etc cp up are given by cj equal to y dot uj divided by uj dot uj for all j equal to 1 etc p. So this is the theorem. You should remember this theorem, and the proof of this theorem is that uh, in this proof, orthogonal basis proof, what we have done is we have uh, we have calculated, or we have computed the uh, coefficient values c1, c2, c3, etc. cp values by dot producting with u1, u2, u3, etc. up. Right. So the same concept is here also. That means y dot uj divided by uj dot uj. Okay, y dot uj divided by uj dot uj. That means cj. That means, for example, here the orthogonality of set as u1, u2, up shows that yes, y dot u1, y dot u1, y dot u1 equal to c1 u1 plus c2 u2 plus etc cp up dot u1, that's equal to c1 into u1 dot u1. That means in the previous proof uh, we have assumed that this y is equal to 0, but in this case this y is not equal to 0, y is not equal to 0, but y is as it is. Y is some non-zero scalar, non-zero real number. So what happens is you yes, y dot u1. So 0 dot u1 means here y dot u1. So y dot u1 will be equal to yes, this c1 u1 plus c2 u2 plus etc plus cp up dot u1. That means equal to the same reduction technique you have to apply, which is applied in the case of 0 dot u1. 0 dot u1. So that means you will get, finally you will get yes, this 0 equal to c1 u1, c1 u1 dot u1. That means here y is equal to y, here y will be equal to c1 into u1 dot u1. That means yes, y dot u1 will be yes, y dot u1 will be equal to c1 into u1 dot u1. So hence you will get the value of c1 as c1 is equal to y dot u1 divided by u1 dot u1. Right. So this is the technique used to compute c1, c2, c3, etc. up to cp. So this discussion can be extended for any coefficient c1, c2, c3, c4, etc. cp in coefficient. Right. So that means in general you can say that cj will be equal to y dot uj divided by uj dot uj for every j equal to 1, 2, 3, etc. up to p. Yes, that is our. So yes, since u1 dot u1 product u1 is not 0, the equation above can be solved for c1. To find cj for j equal to p, compute y dot uj and solve for cj. So that is our yes method of calculating the coefficients of C1, C2, C3, etc. Cp. Okay, so why we calculate this coefficients C1, C2, C3, etc. Cp is because we have to find out the orthogonal basis for the first case study. Now we will explain this by an example. That is, set S is equal to U1, U2, U3. Okay, in example 1 is an orthogonal basis. Just that we have proved. Orthogonal basis. Set S equal to U1, U2, U3 forms on an orthogonal basis for R3. That we have already proved. Now express the vector y equal to 6, 1, minus 8. Y is a vector, and it belongs to R3. That means actually this y belongs to W. That means a subspace. This y equal to 6, 1, minus 8 is a point in 3D space. And this the set of for such points is R3, our 3D space. So that is the subspace spanned by S. Okay. Now express the vector y equal to 6, 1, minus 8. Our question is, the examiner is asking you to find out an expression or a linear combination of the vector in S. Okay, a linear combination of U1, U2, U3. Y is expressed as the linear combination of U1, U2, and U3. The examiner is asking like this. That means you should find out C1, C2, and C3. That is indirectly what the examiner is asking you to find out. So the yes, solution will be like this. Yes, you are applying the basic formula, that is nothing but Cj will be equal to y dot uj divided by uj dot uj lj equal to 1, 2, and 3. So you apply this, so then you will get this y dot u1, y dot u2, y dot u3 you will find out, and also u1 dot u1, u1 dot u2 dot u3 dot u3 also you will find out, and y is equal to this, like this. Okay, so that's our expression. Yes, we find out C1, C2, and C, and put it in the equation, that is y is equal to C1 u1 plus 2u2 plus C3. So you will get the expression of y. Okay. Now moving on to the next topic, very important topic, that is orthogonal projection. Let us consider a vector, a position vector in 2D space. 2D space means we have x-axis, y-axis, then here it is minus y-axis and minus x-axis. Now a vector, a point, a vector in 2D space, that is E. So I have the vector like this, like this, and this vector. So now the yes, we know that uh, we can resolve this vector OP, vector OP into two uh, two vectors which are perpendicular to each other or orthogonal to each other. That means like this, we have two vectors, two orthogonal vectors. That is some Q R. So OQ and OR, the two orthogonal vectors of this identity each other. So two orthogonal vectors uh, can be, so this strong vector P, vector OP can be equal to OQ plus OR. Or in other words, this OP can be solved two vectors which are orthogonal to each other can also. So that so these are known as orthogonal projections of vector OP. So and what are the orthogonal projections of vector. So this is very familiar in R3. Similarly, R3 in R3 also you can find sort of projections like, for example, speeds like x axis, y axis, and p. Then this vector p can be written uh, vector as a sum of the three vectors which are orthogonal. This vector can be solved for the orthogonal further is such that the sum of all so this concept can be extended to any field, any dimension, right? This concept can be extended to fourth dimension, fifth dimension, sixth dimension, seventh dimension, etc. N dimensions. So we are going to define or we are deal or solving of vectors with R. That is our let us let us consider a yes, a non-zero vector in R. Let U a non-zero vector that which is not equal to zero vector or a non-zero vector in which belongs to R. So with U in R2 will be in xy plane. Xy plane will be like this. For example, this is for example a non-zero vector. A non-zero vector. Okay. And in R3, it will be in a xy and z 3D like xyz like so that will this is okay. Like this a non-zero vector I am considering right in Rn. General I am saying it as Rn. so this is a vector like this vector. Okay. Now if you multiply this vector u with a scalar some alpha, let us say it is alpha. So alpha into u, alpha u. So if you take alpha equal to 1, 2, 3 for any scalar minus 1, minus 2, minus 3 or minus 1.1. So like any scalar, then what will happen is your the length of u will vary like this. Positive direction like this if you alpha is positive and etc., or negative direction like this if it is alpha is negative like this, right? It's in a straight line. So that is what your alpha is. Now I'm considering another vector which is z, which is z, a z vector, and this z vector is exactly orthogonal to, that is perpendicular to this alpha u or u. You can say just u. So z and u are orthogonal. Now I am considering another vector, y, another vector y in the same R. This is Rn plane. Okay, I am considering this board, the entire board as the Rn space. So these all these alpha u, z, y, all these are vectors in R. So I'm considering another vector y, so that I can generate this y. I can give rise to this y vector like this, alpha u, yes, this is alpha u and z joined together, get another vector. Okay. This is my E. That means y equal to some y cap plus z, where y cap is equal to alpha. Okay, this is my E. So this is known as the, so or in other words you can say that this y vector can be decomposed. This vector y can be decomposed into two orthogonal vectors, two vectors which are perpendicular to each other, that is alpha u and z. Okay. Yes, that is my that is what you call it as orthogonal projections of y. Z and alpha u are the orthogonal projections of y. So how it happens, that we will discuss this uh, in this session. Now here, yes, y cap is alpha u and z is some vector orthogonal given in scalar alpha, and like z equal to y minus alpha. Okay, that means this z, that z equal to, z is equal to y minus alpha, so that this is our equation 1, okay, and this is equation 2 and this is equation 3. So if you put z in 1, okay, you choose vector z such that equation 1 is satisfied, that is y equal to y cap plus y minus alpha u, and you substitute for y cap, that is y equal to alpha u plus y minus alpha u, so that you will get y equal to y. Okay, so that equation 1 is satisfied by taking this z is equal to y minus alpha u. Right. Now, yes, then y minus y cap, okay, y minus y cap, that is nothing but your z as per the equation y minus y minus y cap, y minus y cap is your z. So z is said to be orthogonal to y cap. Z is orthogonal, that is y minus y cap is orthogonal to your y cap, orthogonal to y cap or alpha u, or u can say alpha u and u are or parallel to each other or in the same time. So you can say y minus y cap is orthogonal to alpha u or u. If and only if its inner product, that is y minus y cap, that is y minus alpha u, y minus alpha dot inner product u equal to 0. That means y dot u minus alpha u dot u 0. That means that is that means this the equation 1, that is equation 1 means y equal to y cap plus z. So the equation 1 is satisfied with z orthogonal to u if and only if uh, this alpha is equal to y dot u divided by, if this is satisfied, this y dot u divided by u dot u. If alpha is equal to this, alpha is a scalar number. Alpha is such a way that it satisfies this equation number 4, that is y dot u divided by u dot u. If that is satisfied, then only you can resolve this y vector into uh, alpha u and z, that is y is equal to y cap plus z. If you are able to, if this equation 1 is to be satisfied, then alpha must be scalar or a real number in such a way that it should satisfy this equation number 4, that is y dot u, that is inner product y dot u divided by u dot. That means, and also yes, and also y cap is equal to alpha u, alpha u. That means y cap is y cap is equal to alpha u, and you substitute for this alpha this equation, then we will get y cap equal to y dot u equal to u. Okay, so the vector y cap is called the vector y cap is called the orthogonal projection. Orthogonal projection of y onto the vector z is called the component of y. The vector z is called the component of y, which is orthogonal to this orthogonal. That is what I mean by orthogonal projection. Orthogonal projection of y onto. Okay. Yes. That means is the definition. So our conclusion is that you can let y be any vector in Rn, belongs to Rn. That means it is Rn means n is 1, 2, 3, 4, 5, 6, etc. up to n. So let y be any vector belongs to Rn. Then this y can be resolved, or y can be expressed as the sum of two another vectors, which are again in Rn. One is the orthogonal projection of y, or one is called the orthogonal projection of y. That means the y cap, and the other is the orthogonal, the vector orthogonal to the orthogonal projection of y. That means the vector orthogonal to the y cap. Yes. So that is our conclusion. Yes, that is orthogonal projection of y on and the vector z is called the vector z is called the component of y orthogonal to u. Component of y. So let y be any vector. So you can decompose that vector into two vectors, which is one vector is known as the orthogonal projection of y, orthogonal projection of y on another vector u, and uh, the second vector is known as the component of y, component of y orthogonal to the first component. So, so that means any vector can be solved into components, and the first component is orthogonal is known as the orthogonal of y, and second component is component of y is orthogonal to the first component. So two components which are orthogonal to each other can be created from any vector y. So the concept is as simple as this. That means, for example, there is your y cap, is equal to alpha u. Let this alpha is replaced by the scalar c. C belongs to a set of vectors. So now y cap will be equal to c. Right? Then vector u, for example, suppose u belongs to R2, which means we have x and y coordinates, and our u will be like this. U will be like this. Okay. Then Cu means C belongs to R. So Cu means you have for different values of C ranging from minus infinity to plus infinity. If you vary this value for C, then you will get so many vectors, an infinite number of vectors like this. Also in this direction. So like this, like this also. So then this is known as our this this uh, these vectors. These vectors are our spanned vectors. That means generated vectors. Okay, generated from the vector u. That is by giving different values for c, then you will get a large infinite number of vectors which are along the line of u. Right. So this you can say span. This these set of all vectors can be considered as the subspace subspace spanned by spanned by or generated by the vector u. So you can yes it's not there is no doubt that the u vector generates all these vectors by varying this scalar quantity c. So you can say that these set of all vectors can be considered as a subspace which is spanned by vector. Right. Now this y cap which is called as the orthogonal projection of some other vector y, and this y cap belongs to this subspace.
belongs to the subspace spanned by this. Spanned by this. So, you can say that, yes, you can say that the any vector y, okay, any vector y, it can be resolved into two vectors, and the one vector will be a vector in the subspace, a vector in the subspace spanned by u, spanned by the vector, and the other vector, other component of that vector, vector y, will be perpendicular to that subspace z, perpendicular to that subspace which is spanned by u. So that means I'm taking this span of u. I'm considering this span u equal to some subspace w. So that means the second component of y will be perpendicular to this subspace w. That means z will be perpendicular to w. So that means you are resolving any vector y into two components, where the first component is in subspace w, that is y cap, which belongs to w, and the second component is z, and that will be perpendicular to the subspace w. So that's the idea. So the subspace spanned by u will be a line like this, a line or a set of all points in this line passing through the subspace w. Okay. And again, the y vector can be resolved into two, where the first component will be in the subspace w, and the second component will be z, which is perpendicular to subspace w. Now we are going to have that equation, that is projection, orthogonal projection of y, onto the subspace L. Here in my explanation I have named it as w, but in your textbook it is named as subspace capital L. So this y cap is called the orthogonal projection, okay? Orthogonal projection of y onto L, and it is given by this formula, which is very similar, very similar or exactly equal to our finding coefficients, C1, C2, C3, etc. CP formula. Okay, that means y dot u divided by u dot, okay, into u. That means this is like alpha u, where alpha is your coefficient, that is real number, that is y dot u divided by u dot u. That into u, alpha u. So that is your projection of projection means not just projection, it is orthogonal projection of y onto the subspace L, and it is denoted by y cap, or project L y equal to this equation. This is our equation. Now, yes, so now we will explain all these discussed concepts with a sum. That is, let a vector y in R, okay, be given by this matrix, and u is given by 4. Then the examiner is asking to find the orthogonal projection of y on, and he is also asking that how to write y as the sum of two orthogonal vectors, one in span u and one orthogonal u. That means y you have to write y equal to y cap plus z. You have to find out this y cap and then z. Y cap is uh, y cap will be in span u and z will be orthogonal to span u or orthogonal to, right. So the solution is like this. First of all, compute. We are going to apply the formula. This formula, that means y cap. You have to find out by this formula. That means y by u divided by u by into u. First of all, you just find out that is y cap. Okay, right. Then you will have to find out what z. Z actually y equal to y cap is that. So z equal to y minus y cap. So y minus y cap is this. So you find out y cap and z. Then yes. Then you are going to represent the y as sum of y cap and z like this. And then yes. So this decomposition of y is this of that figure will be like this. Right. So this is our in x1 x2. So this y is decomposed into uh, to yes, this y cap and this y z. And L is the subspace spanned by 2. So that is orthogonal span. So y cap is a vector which belongs to span, right? So then yes, yes. So we are verifying that the calculations above are correct. Then y cap and z will be orthogonal to each other. That means their inner product or dot product will be 0. That is also verified here. So yes, this yes, in our question we have to find out the orthogonal projection of y onto u. So that we have find out. So that is solved. Then write y as the sum of two vectors. That's also that. So that is our sum. So hope you understood all the concepts we have that I taught this video. Right now, so clear it as soon as possible.